I'm going to start showing you how to use Python and Cantera in preparation for homework 3 and for your computer projects. You've followed the instructions and have installed Python with Cantera, and you fired up Jupyter Lab, but you can also fire up Jupyter Notebook, and these are explained very well in the Cantera website. So, introduction to Python is that to use Python, you first need to import a bunch of modules. So I guess in Jupyter here, the notebook is divided into little blocks called cells, and a lot of these cells have actual code that you can run and execute commands. And to a certain extent, this is a bit like either a Matlab or Mathematica or Wolfram Alpha if you are used to those. And so with Python, it's a very flexible language, and after you get the hang of it, you will realize it's a little bit like Matlab, with some differences, of course. But best of all, it's free, and it'll do everything that we need to do. But with Python, you need to load a whole bunch of packages. With Matlab, they're sort of loaded by default, I think. And so for Python, you need to explicitly load them. So say if you want to import Cantera, you can use the command import and then the name of the package, and then if there is the as afterwards, this means that basically the CT will be shorthand notation for Cantera. So if you want to use Cantera instead of typing in Cantera every time, you just need to type in CT. Math has all the math, has the major math functions like square root, stuff like that. Optimize package has routines for finding maxima and minima of functions, solving linear equations using fsolve, which you've probably used in Matlab. You can do nonlinear curve fitting, and SciPy integrate. That has all the differential equation solvers that are similar to RK45 in Matlab, and it also has a numerical integration like say traps, things like that. PyPlot or Matplotlib gives you plotting things that's very similar to Matlab. NumPy gives you nice arrays and some array-like functions. And all sorts of other things. And so at the top of all of my Jupyter notebooks, I import a whole bunch of things. And if you want to execute a block, you hold Shift and push Enter. And then you see I did that. I held Shift and I pushed Enter. And so that's how you import a bunch of things and execute a block. So first we'll get to Cantera after some Python basics, and the math module, which was imported right here, has some mathematical functions like square root, exponential, log, etc. And these are used in a Python class. So you're actually importing a Python class, and the square root is a function that is inside of that class. So if you want to call a function that's inside of a class, you have the class name dot the function that it's the class name dotted with the function name, or the shorthand name such as CT for Cantera dot with the function name. So if you want to take, say, the square root of a number, and you're using the class math, the class name would be math, and the function name would be sqrt for square root. So here I have an example box here where I'm just using math, and I'm using the print command to basically print their output. So I want to use square root, so it's math dot square root, and then the number, then exponential, log. This would be the natural logarithm, and log 10 is a log base 10. So I hold Shift and push Enter, and then I get all the outputs here. So log 10 of 10 is obviously 1. Okay, so and you can do some standard mathematical operations For instance, if you want to exponentiate things, it is not the caret symbol. It is not the caret symbol. What I mean by the caret symbol is this sort of up arrow thing. It is not that operator. It is a double star like Fortran. So, for example, if you when we'll go over this actually burning law later, but the burning rate of a propellant is given by Saint Robert's law, and Saint Robert's law states that it's given by a constant times pressure raised to the nth power. So, if you want to compute the burning rate, and you know the prefactor, you know the burning rate exponent, and you know the pressure, the formula that you punch in is A times P, and then to raise P to the n, you would then do P double star n, and then if you wanted to print that, you could just basically you can put strings inside of print commands, and then the RB, and if you're worried about the format looking nice, you can put in similar formatting strings commands like you do in Matlab. Okay, and in Python you can also define functions. For example, we could define this sort of cubic polynomial here, and we're going to define a function to evaluate that, because say we need to evaluate that 10 million times. We certainly don't want to type this out 10 million times. We just want to call a function that does that. And so, going to do a bit of a numerical trick. You can prove it to yourself that this is the same, but I'm going to rearrange this into what's called Horner form, and that's a very expedient way to do this. It really saves the number of multiplies, because this has 1 multiply, 2 multiplies, another one for the squared, 3 multiplies, and another 2 for the x cubed. And so this has a whole lot of multiplies, where this has only 1, 2, 3 multiplies for the whole thing. And so it saves many multiplies. And so if you want to define our function, I'm just going to call it a poly. So you would do def, the name of the function, and then all the arguments to the function. So this would be the x value, and then the value of all the polynomial coefficients. Then you would basically end this line with a colon, and then then everything below the column is executable code that is in the definition of the thing. And now how Python decides whether you are inside of a function or a loop or something like that is by the level of indent. So basically right now, if you are indented inside of here, this means that basically this term value is computed inside of this sort of poly function. And then if there's a value that you want to return, you just type in return and then whatever you want to return. Okay, and so here I'm just going to I've defined this the return value for this polynomial, and then in this line here I'm just going to write its output. The function value is, and I'm just going to use the polynomial with these with the x value of 3 and these polynomial coefficients. Okay, and so note that when you break the that the first line that basically moves to the previous level of indent, that means you are now outside of this function definition. So in other words, these lines here are all part of the function, and this line here is a separate executable line of code. Okay, and so basically these 3 lines are defining the function, and this line here is using that function. Now you need to be careful with this indent. Python is very picky about it. Say if I move this in here, it would probably not work. And see, it says it gives an error expected and indented block. It does not like that. So I'm going to tab back out. If I where if I were to use an extra space, it would it would not work, as I get this I get this indentation error here. If I do them both at the same level, it will work just fine. But it's sort of good practice to use to not use spaces, but to use tabs. And so the default tab is about four spaces. So you can see that it'll basically scream it'll basically turn red and scream at you if you're not following these sort of quote unquote Pythonic standard. Okay, and so in terms of getting in terms of getting used to MATLAB, transitioning from MATLAB to Python, that's one of the most difficult things to get used to. But the thing that makes it nice is that this indentation concept for determining whether you're inside or outside of a function, it forces you to write nice looking code, which makes it nice for you 3 months from now if you want to look at this code to down the road, and it makes it nice for your instructor to grade everything too. Okay, and so these functions here, it's actually they are automatically vectorized and can be plotted very easily, very similar to MATLAB. And so the plotting library was called Matplotlib, and we imported that as PLT. I'm going to scroll back up to the top. So we had a matplotlib.pyplot as PLT. So if we want to use those commands, we don't need to type in this big long matplotlib.pyplot. We just need to type in PLT. Okay, and so we are going to plot our polynomial here, and we're going to plot it over 100 points. And so here we're just going to define a number of points, and are going to define the polynomial coefficients. And in MATLAB, if you're going to initialize an array, there are very nice linspace and log space functions. And so what we're going to do, so then basically what we are going to use is the linspace command. And that is part of the NumPy package, which we imported as np right here. And so basically the command would be np.linspace, and what linspace is doing is it is defining a sequence of evenly spaced numbers that basically start at the value over here. Start and then end at the value over here, and then the number of points is basically this argument here. So as written here, we are basically having points that start at -1, end at 1, and we're going to use 100 evenly spaced points because that's what we defined num points to be. And then we are going to define y as an array, and it's just going to be the output of the polynomial command, and basically it is automatically vectorized. So if x is an array, it basically knows what to do with it. And so then we're going to take x and y, and we're going to use the plot command. This is just like MATLAB. So you plot x and y, then you can do the x and y labels to make them look nice. And then one thing is that you have to explicitly show the plot. Okay, so I'm going to run this, and you can see I get a nice looking polynomial plot. Okay, and so that is one way of doing it. And the other way that you can do it is you can plot the old-fashioned way, like you probably first did with MATLAB, is that you explicitly made an array, and then using some sort of for loop to fill the values of that array. You can do that. I do that all the time too, because it's not always you don't always have a super nice function like this, and you need to do something much more complicated to fill them. And so now note, this is one thing you need to get really used to too, is that Python arrays start at an index of 0, which is sort of, if you have experience with C or C++, all arrays in C or C++ also start at 0. But remember, MATLAB would start at 1, so if you're used to MATLAB, it does take a bit of adjusting to get used to the fact that arrays start at 0, not 1. And so if you specify an array with 10 elements, the range will be from 0 to 9, not 1 to 10. Okay? And arrays are defined with a square bracket. Okay? And so, and I find that to be very nice. So if you want the if you want value of array 9, that would be the 10th element of the array, because remember they start counting at 0. You would just say the command would be oops, gotta run this again. The command would be the name of the array, square brackets, and then the value that you want to pull out. And basically, function arguments are defined with a parentheses. So it would just be function and then a parentheses and then all the input arguments. And that makes it very nice, because in Matlab you can't always tell, because it uses basically rounded brackets for both. And you don't know, and if you're new to somebody else's code, you don't know whether you're basically whether you are calling a function or grabbing an element of an array. And so that makes it really nice. With Python is that basically they use different symbols. And also similar to Matlab, you can grab entire sections with the colon operator. Those work the exact same way, so I'm not going to go over those. You can skip over elements, and you can count backwards, things like that. Okay, and so here I'm just going to just give examples of this colon operator in action. Here, so I'm just going to define an array of 10 point sets that are numbered between 1 and 10. And so I'm going to print the entire array is exactly what you would think. And notice that when you just have it print an array, it puts it in square brackets. And so here, this is something you have to get used to, is remember it is 0 based. So basically if you're grabbing element 2, you are not grabbing element 2, but you are grabbing but you are grabbing 3, 4, 5, and 6. Okay, and so and that's one thing too that you need to get used to, and you just need to play with it a bit. Okay, and so I'll play with this. You'll see in my sample codes I use the slicing operator all the time, because it is much faster to use the slicing operator when possible versus a for loop. Okay, and so as I said before, now we're going to go over looping and if statements. And so here we're just going to define a function here. Here we're just going to fill in our x and y values the old-fashioned way. And so we're just going to fill it with 10 points. And so here I'm just going to do the x array. This is just alien space from -1 to 1 over these 10 points. And then I'm going to define a y array with just a bunch of zeros. This is pre-allocating for those of you who use Matlab quite a bit. Your code will be a lot faster if you pre-allocate everything. Okay, and there are various computer science reasons for it. Okay, and so now what we're going to do here is we're going to loop over each element of this x array, and we're going to fill y using our function for the polynomial that we just wrote above. Okay, and so in Matlab, the code would be for I equals 0 to num points minus 1. Y array of I is equal to our function x array I a b c d, and of course it's Matlab, so I would have to start at 1 and basically end at num points. But the for loop would in Matlab would look something like this. In Python, it looks something like this. So here I'm just having it print I, so we know where it's at. And so here Python is actually quite expressive. So you just write for I in the range of num points, And so I would be, I is your dummy loop counter, and you're just saying I, and it's in the range of num points. Okay, so it's going to go from 0 to 9. Okay, and so we will do this, and then it's gonna print what value of I is there, and then it's going to fill the ith entry of the array. Remember, it's square brackets. The input argument to our polynomial function is going to be the ith value of the x array, and then I'm going to take those results and then plot them on top of that line that I plotted earlier. Okay, so we will execute it. So notice it's a simple for loop, so it's just printing I. So I have I 0, 1 through 9, and then it filled the polynomial. And here I am plotting the 10 points here that we filled in manually as a bunch of red stars. Okay, so that's how that works. So that's for loops. Again, remember the level of indent is what's determining whether you are inside or outside of the loop. So if I was to unindent this line, the code will probably be broken. And you can see that because I stopped at 9, so what happened here is it preset all the y values of the array to be 0, and I moved, okay, and so basically they're all 0. And now I moved this line I moved the level of indentation out so that it is no longer in the for loop. So now basically what it's doing is it's looping over I in the range of num points, and it prints it to the screen. But it does nothing after that. So after it prints it to the screen, it just goes back up and it grabs the next value of I, and then it prints that to the screen. And so then after we're out of the number of points, I is 9. And so here only the very last value of the y array, which is 9, is being filled properly. Okay, and so that's why I here is still 9. And so that's why this very last point is filled properly, but all the others are 0. So you do need to watch out for things like that. And also, again, watch out for the space thing. If I were to do this, it would break. But if I move the top print in, it works just fine. But again, it does not like that. So again, just get used to doing this. And this does make the code look nicer. I've seen some really messy looking Matlab codes, but this here sort of forces you to write a fairly nice looking code. Okay. And then you can also nest multiple for loops and have if statements in those for loops. So again, we have for I in range num points. I just have num points here to be 3, and then inside of that I loop I have another j loop, and then for each j I'm just going to print something different here. And so basically this level of indent here. That's at basically this level here. This is all basically these commands here are all inside of this upper I loop here. Then I have another for loop, and so these lines here are all being done inside of this j loop here. Okay, and so notice that the for loops, just like the function definitions, they end with a semicolon. Then I have to do if statements. Again, you just do if and then end it with a colon. And again, the commands in the if statement again are determined by the level of indent. So it's the same way. Okay, and so basically, this line here is inside of this if statement here. This line here is inside of this else if statement here. And this print statement here is done in the else, and this print, and then this final print statement here. This is associated not with any of the ifs, because we have indented out, but it is part of the J loop. Okay, and so we just run this command and you get the rather boring, just all these print statements, but it's just showing you how to how the level of indent works for basically nesting for loops and things like that. Okay, so that's the basics of for loops. Again, you just need to play with them to get used to them. So one thing I will say with Python is that arrays and lists are pointer based, and this can lead to some really frustrating bugs. But there's a pretty easy way to get around all those bugs. You just need to get in the habit of doing it. However, in this class, you shouldn't run into these too much, but you never know. So first, if you define an array with NumPy, and again, as I said before, it has you can set the arrays like you would with Matlab. But what Python, how it's storing the memory is it's actually a pointer to a space in memory. So basically, this var command is initializing just a bunch of data in the memory, and this linspace command is basically telling you it to basically evenly space in between 0 and 1. And I'm just making a copy of that variable because we want to do something later on with it, and I'm defining some right hand side here. Okay, and then ones just makes it all ones. Okay, so say you naively want to copy, basically run this command here, and you want to take whatever is in this array here and copy its values into its var copy here, because after all, you defined a var copy here. Well, what this command is doing is it's not doing what you would intuitively think. What it's doing is it's actually erasing the var copy that you made here. It's erasing it, and instead it's now defining it as a pointer that is pointing to var. So basically what it's saying is that var and var copy are the exact same thing, okay? And so they are not two different arrays that happen to have the same values. They are the exact same thing. So if I change var copy here, I will also change var, and so that's something that you really need to get used to. Okay, and so I have an example here where I do the linspace, and the original values of var are this, and the original values of the copy are the same because I've initialized them the same way. Now what I'm going to do is I'm going to add a right hand side to it, and I'm going to define var as just basically var plus plus that right hand side, okay, which is 1. So I'm just so the updated var is basically all of these elements plus 1. So, but I've only modified var. I did not directly modify var copy. So var is behaving like I would, but when I plot or when I write the array elements of var copy, they are the exact same as var. And the reason they are the exact same as var is because this command here basically told Python that they are the same thing. Okay, so if I change var, I change var copy. If I change var copy, I also change var. Okay, because this command here means that they are the same thing. Okay, so that's something that you really need to get used to. Okay, so how do we fix this? So here I got roughly the same command, but there is a special command that's available with NumPy that you can use, and that is np.copy, and so that will tell it not to basically not to make var and var copy the same thing, but to make var copy its own separate array, and you're going to define the values in this copy as the same numerical values in var. Okay, and so if I do so now here I am only modifying var, and I'm not modifying var copy, and our goal here is to have var copy be unchanged. So if I run this, I can see that the basically var copy, the original entries are here, and after after I've messed with var, they are still the same. Okay, and so that is one way to do this. The other way to do it, and the way that I normally do it, is like this, where I use the slicing operator, and this works only if you have var copy already defined. This is explicitly telling it. This is not saying that var copy and var are the same thing. This is telling it to copy all the array, to copy the data over, and not the entire thing itself. Okay, so if I do this, this will also work just fine. Okay, and so that's something that you do need to get used to. But again, it's just small things. And so SciPy, or Python can also be used to do all sorts of common numerical functions, like curve fitting and like integrating things like that. And that's available with the SciPy package. And the SciPy is extremely powerful. It can optimize curve fitting, find roots, etc. So, it can also solve ODEs, do numerical integration, etc. So here I'll just give an example of curve fitting. So here I have data. This is of detonation cell sizes, and we will be going over that stuff a bit later on. And so it's just the detonation cell size as a function of pressure. And here I did the plot on a log-log scale, so you get you see that it's a nice straight line in log-log space, meaning that the detonation cell size would be a power law. Okay. And so to do a curve fit to this data, we first need to define our function that we want to fit the data to. And so again, notice this data fits a straight line as a function of pressure in log-log space. So we will define our function parameters to be a power law. And so what I'll do, I'll define a function called cell size, such that basically the x value is p, because it's a function of pressure, and we just want a power law. So it'd be a constant times pressure raised to another unknown constant. Okay. Then we basically want to use the curve fitting function to find the optimal A and B to get to basically fit this data. Okay, and so that would be done with the optimize curve fit command. So we have optimize.curveFit. That was part of SciPy, and so this here is the name of the function right here. And p would be the argument, would be the sort of x value of that function, and data is the remaining the remaining arguments to that function. So the function that you are going to curve fit to, the first argument should always be sort of x, and the other values should be the unknown parameters. Okay, and so here, from data we need to extract, and so yeah, we need to do that. And so basically, this will basically optimize the curve fit, and data is the y value of the raw data, and p are the pressure values, and it's going to curve fit the data, and it will basically know what to do with this, because basically it's going to treat the first entry as x, and then basically all the other entries as just as the arguments to them, and it's going to mess with those arguments in the function to basically find the optimal A and B. Okay, and so the optimal A and B's will be basically here, and they're stored in an array. And so A will be the 0th index, and B will be the first index. And this would be the this would basically be sort of the the error of the curve fit, or the R squared value type stuff is with pconv. Okay, and so now we will basically now plot this power law on top of the data, and so that's basically what I'm doing here. So I'm just defining our three, because we know it's a straight line in log space. I'm only going to define 3 points. So I'm going to space the points logarithmically, and so this is spacing a point between 10 to the minus 2 and a point from 10 to the 1, and it's going to use 3 points. And then I'm going to compute the data. I'm going to compute the y values using our cell size function with these basically with these y values here, and our optimal A and B. Okay, and then I'm just going to plot them. Oh, forgot to run this. Now it'll run. Forgot to run this. Now it will run. And so you can see that we've basically found a nice line that basically cuts right through the middle of the data. Okay, and you can do really nonlinear curve fits with this. It's actually really powerful after you get the hang of it. Okay, solving ODEs, that will be important for homework 3. This is very similar to Matlab, where first you need to define a function for the right-hand side, then call an ODE solver. So the first example will just be doing a forced spring mass damper system that has the second order differential equation my double prime plus cy prime plus ky is equal to a forcing function here. And so I'm not gonna go through how we basically turn the second order ODE into 2 first order ODEs. You guys have probably already done that either in your vibes, or you guys have done that in your vibrations classes back in the day. But basically, like MATLAB, SciPy, and Python require that you have an array of first order differential equations, and those are equal to basically some some right hand side function, which is also an array. And so for our spring mass damper system, the second order ODE turns into two first order ODEs, where basically y.1 is just the velocity, so the time rate change of distance is just the velocity, and then the acceleration is equal to our function here. And so basically here I'm going to define this right hand side function, and then I'm going to integrate this basically using SciPy. And so this part here is almost identical to what you would do with MATLAB for the exact same thing. So here I just have the mass, spring constant, mass, spring constant, damping coefficient, amplitude of the forcing function, and the frequency of the force. Okay, and then time and y. And note, time and y do not have to be the first and second indexes. So the first thing I like to do is I just like to take the array, and y is an array and t is time. And so the first thing I like to do is I like to just grab the elements of y here, and then basically just copy them over into what I've labeled them in the right hand side function, just so it is easier for me. Okay, and then I'm going to compute the right hand side. So dy dt for 1 is just equal to y2, and y2 is just y1. I should have just done it like this to be explicit. Okay, and then I'm going to call this, and so basically y2 dot is equal to basically this mess here, and I need the sine function, which is available in math, or even NumPy has a sine in it, and that will work just fine. And then I'm going to return an array where the first index is basically this one, and the second index is basically y dot 2. Okay, so this is very very close to what you would do with MATLAB, except for these things would be up here in the definition. Okay, but that's mainly that's the main difference. Okay, so I'm going to run the function. So this right hand side function has now been defined, and so here I'm just going to set a mass, a spring constant, a damping coefficient, a frequency, and then I'm going to basically integrate this ODE. Okay, and so so we solve the ODE. This is very similar to ODE 45, ODE 320s, etc. And so I'm just gonna basically skip through this. And so here we define a solution as integrate.solve IVP, or solve initial value problem. That is an ordinary differential equation. So here I'm going to use what's called a lambda function. Don't be confused by that. This actually makes it really super easy. And so you just define a function as lambda, and it's going to take time and the y value, and it's going to call and it's going to take them after the colon in our function, which we defined as right hand side. And so it's gonna use time as t and y as y, and then it's going to call the sort of right hand side function, and it will basically look for time, and so time and y have to be similar in this function argument, but all the other function arguments, mass, the damping coefficient, are going to be based on what is up here. And so this makes it really nice to have other arguments to your basically to your right hand side function. At least back in the day, but with MATLAB this can be really cumbersome. At least back in the day, when to do this you had to define all sorts of global variables and things like that. And then also back in the day, MATLAB functions had to each be in their own different file. So basically, if you had many small functions, you would have dozens and dozens of files that had a bunch of 2 or 3 line functions inside of them, so it became super cumbersome. But now with these lambda functions in Python, this becomes really easy, because you can add as many function arguments as you want, just so long as t and y are 2 of them. Okay, and this lambda function just basically lets you do that, and you don't have to have any specific ordering of t and y and things like that. They can be anywhere. Okay, and so I'm going to integrate them. The time span is going to be from 0 to 100. The initial conditions are going to be the initial position is going to be 0, and the initial velocity is going to be 1. And then I'm going to use RK45 as the method. Okay, and so I'm just going to run it, and then I'm going to plot the solution or the position. And so here I get this function that looks like this. Okay, and so this doesn't look very nice. If you remember from dynamics, this is a sort of beating frequency here, and I don't have and it should have a nice little almost sine pattern here. And here what's happening is that the ODE solver is going there's too much error in it, and it's not getting that nice upper curve. So basically I'm going to change the error tolerances. This is something that you should have learned with MATLAB, but it's not always gone over. So I'm going to repeat the solution to the ODE, but I'm going to tighten up all of the error tolerances a bit more. So I'm going to use a relative tolerance and an absolute tolerance of 1 times 10 to the minus 12, and then I'm going to plot the solution. It's taking more time because it has a lot more points to go through, but here now I have a nice, really high quality solution. It's not as jagged as the one here, but it's now a nice, really high quality solution. And so just sort of keep that in mind if you need a high quality solution for anything. Okay, and so that's basically how you integrate an ODE. That's a nice ODE. It's a nice normal ODE. But we work with chemical kinetics, and we'll be integrating systems that are called stiff. And so here is a system of ODEs that arise from what's the so-called Robertson kinetics, which is a toy chemical reaction network, where we have A goes to B, 2B goes to B plus C. B is kind of acting like a third body here, and then basically B plus C goes to A plus C. Okay, so if we use the law of mass action here, we have the time rate change of the concentration of A is minus K1 times A plus K3 times the concentration of B times the concentration of C, and so forth. So if you apply the law of mass action to here, you can basically back out these rates of production. So if we want to integrate the system, we basically wind up needing to solve three coupled nonlinear differential equations. So again, we need to define a right-hand side function, and basically A will be y0, B will be y1, and C will be y2. Okay, so I define our right-hand side function. Note they have to have t in some solution vector as two of their inputs, and then basically any other argument that we need. So for this chemical reaction mechanism, we will be treating K1, K2, and K3 as constants. They are not going to be functions of temperature. Okay, and so here I basically just form this right hand side. So I got dA, dB, and dC right here, and you can see it just basically follows the format of this array here for the right hand side, and then I just return them. Okay, so that's just like basically like the ODE solver. And so now this is a so-called stiff system, and so we need to use a completely different numerical method for basically integrating them. So for the mass damper system, we used the equivalent of ODE 45 in Matlab by using RK45. That method will not work well for these. It will basically wind up taking billions and billions and billions of very tiny little steps. Okay, and I'll show you what I mean by that. Instead, here we use what's called a stiff ODE solver, and I'm going to use. Oops, gotta run this again. I'm going to use a method called LSODA. And then if you want, I'll just show you. I'm going to cancel out of the command real quick. You can rerun the solver with basically with RK45 to give you an idea of how inefficient RK45 is, or OD45 is for this problem. Okay, and so here I'm just going to define K1, and K2, and again I'm going to integrate them using a lambda function. And so t will be t, and y will be our solution vector, and it's going to be inputting those into the right hand side function that I've defined up here. Okay, and it's going to be using the K1, K2, K3 that I've defined over here, and it's the same except for the t span is going to go between 0 and 10 to the 12 seconds. Yes, I'm having it span that far. And the initial conditions are the initial concentration of A will be 1, and B and C will both be 0. And the method will be LSODA. And so this is where I'm changing how the system is being integrated. And you need really tight tolerances here, so I'll show you the effect of choosing poor tolerances for this. Okay, and so I will just run it, and then I'll plot the solution on a log-log scale, because the concentrations can get to very small numbers that are still relevant, and the time scales are so drastically high here. So I'll plot this, and so notice here I see the concentration of A, that just goes down as you would expect. Concentration of B goes up, then goes down, and the concentration of C monotonically goes up. And if I plot only the concentration of B, and I notice, and this here is multiplied by 10 to the 6, I notice that the concentration of B goes up to about not quite 1.2 times 10 to the minus 5 basically like molecules or whatever the units are for this, then and it's there for a very short time. It basically rises at about 10 to that value at about 10 to the minus 5, and then after 1 second it basically depletes and then goes down. And so that's why these systems are called stiff, is that they have very, very, very rapid changes. But during this very rapid change here, A is barely changing at all. Okay, and so that's part of why it's stiff, is that you have some variables that are changing very, very rapidly, and some that aren't doing hardly anything. And so this makes this makes this very difficult to solve. And you need to use these special basically stiff solver methods. So notice here when I solved it, when it is running the command, you'll see a star, and then when it's done, it will basically put the number of the command. Notice when I run it, it is almost instant. If I change it to RK45, which is equivalent to ODE45 in Matlab, notice that it's not done yet, and it's still not done, and it's still not done, and in fact I've run out of patience after a half hour, so it's still not done. If you want to, if you're using Jupyter Lab, if you want to basically stop the execution of a cell because it's taking too long, you can click on the star and then push II twice. Okay, and then basically that means this keyboard interrupt means that basically you are the one who has killed the command, and it's telling you where it got killed, and not surprising, it got killed somewhere in solving the initial value problem. Okay, so we'll put this back to LSODA so we can get back to our really fast solver. Okay, and so that's something to be aware of. If you're using a Jupyter Notebook to kill the kernel, there will be a kernel tab on top. And you can just click interrupt kernel, and that will also stop it. Okay, and so let's just play with the error tolerances here. I'll make them super loose. I'll make them 10 to the minus 3, and we'll see what the solution looks like. And you can see it's now complete. It's complete crap. It is absolute garbage. You could not use this for anything, because basically this is saying is that the allowable error is 10 to the minus 3, but at any given time there are about 6 orders of magnitude between the species that has the highest concentration and the species that has the lowest relevant concentration. And so basically our error is larger than that difference, and so our error tolerance is larger than that difference, and so basically our numerical errors are just killing this calculation, as that they're making it worthless. And so if I reduce the tolerances to 10 to the minus 6, I get a better solution, but it still behaves kind of strangely. So it's still not tight enough. If I make it 10 to the minus 9, it starts to look better. So we start to see some weird behavior at the very end. And if I make it 10 to the minus 12, it will start to work fairly well again. Okay, so it has nice, reasonable behavior. And the reason that you can tell is behaving not very well at this tight of a tolerance here is that the concentrations started to grow without bounds, which doesn't make sense because in our system here, the concentrations, the net concentration shouldn't change. It should be, they should sum to 1 in this case at all times. And so it's behaving poorly. So you need to, when you're solving chemical reaction networks, you need to be careful of that. Okay. And then nonlinear root finding. And so you can you can also do nonlinear root finding. Here I just defined another polynomial function, and here the function to do the nonlinear root function is actually fsolve, and it behaves just like the one you use in Matlab, except for it's part of the optimized package. And so here I'm going to define a function that we're going to find the roots of. It's just a quadratic. Here I was too lazy to cast it into Horner form, But yeah, so we're just going to find the value of the polynomial where a is 1, b is 0, and c is -1. So one of the simplest parabolas that you possibly can. And we're going to find where this is equal to 0. So this always going to, so when you're doing nonlinear root finding, it basically needs to find, it will find where the value of it is 0. So it's going to find where the values of the polynomial are 0. Okay, and if you have multiple roots, depending on where you start the guess, it will affect basically which root it finds. And if you if you do a really bad initial guess, it will basically give you garbage. So you just need to be careful of basically things like this. So basically, the first root should be 1, the second root should be -1, and you can pick between the two just based on the initial guess. Okay, and you guys have all been through this in your numerical methods courses. And we had a location with 0 slope, and you can't start a Newton-Raphson based solver on a location with 0 slope. It will do nothing. Okay. And so it will sometimes give no answers, and so you need to be very careful of where you're starting your solver, things like this. Okay, and if you run into a case like this, you can use a bisection method or a Brent method, and basically those will always find a root as long as you basically set them up right. So I have an example of a command here that does that, and I'll show you that, and I'll let you read that yourself. And then in the sample problems that I've given you for the heat conduction problem, I basically wrote some classes because they'll be very handy for you. And so classes are very handy for wrapping sort of groups of functions where they all work towards a sort of certain thing. So for example, say with our Robertson kinetics here, say we wanted to write a function that computed the maximum concentration of B here as a function of K2. Okay, so basically right now what we would have to do is we'd have to take this thing and then wrap it in a giant for loop, basically setting up all this chemical kinetic stuff all the time. And that would be kind of tedious. And so a more cleaner way of doing it, especially if you're going to use the function a lot, is to define a class. And so here we're going to define a class called Robertson kinetics. And so you just so that syntax is class and then Robertson kinetics. Okay, and then basically everything that is indented one level in from the class are functions and variables that are defined within that class. And so the first command should always be init, and this is a double underscore 1, 2, and then basically these are the inputs to it. So and you'll see how this works when I call the class. And so the first argument is always self. This means it will become clear when you start using it. This is itself, and then these are all the variables that need to be initialized. Okay, and if you see in a function too, if you see a variable in its definition as the variable name equal to some number, that means it is an optional input. If you do not specify what, say, A0 is in the input arguments, it will use 1. Okay, because that's basically what you're saying. And so this initialization function is how you initialize this class. And basically what I'm saying is that by self.k1 is the class, this class Robertson kinetics, which in this function here I'm defining as called self, is I'm defining in this class, in its part of its container is the variable k1. Okay, and that's set to just sort of k1. And so basically this k1 is now permanently stored as a part of this class. And so if you want to basically access k1, it would be whatever you named your class dotted with k1, and then you can find the value of k1. If I did not do this, this k1 would only exist in this function here, and it wouldn't do me any good later on. And so I do all sorts of other little things here. So I set the stopping time, which you can change. The initial conditions can be played with, and I also store a maximum value of b, and then I do a little computational sanity check function here. Okay, and so here what we're going to do is we are going to integrate the same kinetic reaction mechanism scheme, and what we're trying to set this up for is to make it really convenient to basically call that Odes solver for a whole bunch of different values of K2 and find the maximum concentration of B as a function of K2. So we need to have our right-hand side function, and so it needs to be a function of this class itself, T and Y, and this will make sense. And now this K1 is not just K1, but it's self.K1 because it's been stored permanently in our class. Okay, and so then you go through, do it again. So this here is largely the same. And then I have a function called evolve reactions, and that's just dependent on the class itself. And so I'm defining self.solution. This will now be stored permanently in the solution. And I call the same initial value problem solver before. Use the same lambda function approach, but again, it's not reaction.RHS, it's self.reaction.RHS. Okay. And because K1 and K2 are defined as part of this class, which I've called self here, basically I do not need to specify those as function arguments anymore. Okay, and so now this is going to solve it. And then I got various convenience functions for plotting the solution, and then finding the maximum amount of B after the solution has done. Okay, and if it has not computed the solution, if you try to plot something or find the maximum value of B, I set this up to basically scream at you. Okay, so how this works. So we've defined our class. It just basically sets up the parameters for solving the Robertson kinetics, and then you can call various functions to basically integrate them. So here I'm defining RK as the Robertson kinetics class, and so this here is initializing the class. So I am defining RK, and it is actually calling this function right here. Okay. And notice the self here is part of the class. You do not when you are initializing a class or actually using a function inside of a class, you do not explicitly write the self here. The self here would be part of the self dot. Basically, you can think of this self here is actually this first argument here. Okay, but so you don't explicitly list that. Okay, and so here I don't need the self. I only need to explicitly use K1, K2, and K3, and I like all of the other variables, so I'm going to leave them alone. Okay, so then I'm going to do this, and then I'm going to do one command where I try to plot the solution before I solved anything. Then I'm going to solve it. Then I'm going to plot the solution again, and then I'm going to get the maximum value of B. Okay. Oop, gotta run this. Okay, so it first tried to plot it, and it basically printed out my command: kinetics not integrated, no solution to plot. And so basically, this here I have defined Robertson kinetics. I've defined an instance of the Robertson kinetics class as RK. And then I want to call the function plot solution, so it'd be just RK dot plot solution, and the only argument to plot solution is self. So when I call the function, it's basically empty. Okay, because the self is taken up by this RK dot. Okay, so it screamed at me. So now I want to evolve the reactions. So I just call the evolve reactions command. So it's RK dot evolve reactions, and then that solves the ODEs. Now I can plot the solution and get the maximum value of B. Okay, and so the plot solution worked. That looked just like it did before. I might have messed with the K1 and K2 a little bit, so it's plotting just fine. I'm getting the maximum value of b. So basically, all of these commands for basically solving this right here are all boiled into just 4 lines of code. I need to instantiate the class, then call the solver, and then plot. And so it does, and that does all of this stuff. And so that makes it really, really nice. And so now what motivated this is, for whatever crazy reason, I wanted to find the maximum value of b as a function of k2 over a wide range of parameters. So here I'm going to define an array for k2 as np.log space. So it's going to vary between 10 raised to the power 3 and 10 raised to the power 10. And then I'm going to compute for each ODE solution. I'm going to compute the value of b max. Okay, and I'm just going to initialize that to be nothing but 0. So here the idea is I'm going to loop through all of these values of k2, and I'm going to set up a Robertson kinetics class with basically with k2 equal to that particular value of k2 at that instance. I'm going to evolve the reaction using that value of k2, and then I'm going to find the b max. Okay, and so notice here I don't set this. I don't have anything equal to this, and that's because if I go up to the class, the evolve reaction does not have a return statement, so it does not return anything. But this b max function does return something, so I can use it a bit more conveniently. Okay, and so I'm going to call this. This might take a little while. So it's basically running it, but it's running 100 of these, so it's going to take. It's not going to be the quickest thing in the world, but it's basically looping through every one of those k2 values, integrating the ODEs, finding the maximum value of b, and then ultimately plotting it, and then plotting the maximum value of b as a function of k2. And notice here, this is I did multiply this by basically 10 to the minus 6. In here I did not, but here you can see that basically this basically solved those ODEs 100 times, and it found the maximum value of b, and then you can plot things. So this makes it really nice to do some fairly complicated calculations.